let's talk about ellipses. So first we'll talk about how to create an ellipse. We start out with 2 points called foci, plural of focus, and we have a string that's a consistent length, and we grab a pencil and we draw, stretching that pencil, or using the pencil to stretch our strings in such a way that no matter where we move those, the pencil lead, the sum of the two strings is the consistent value, in this case 6.5. Then we create something called an ellipse. An ellipse has a major axis, it has a minor axis, it has 2 foci on that major axis. So we can clear it, change the foci, and then run our pencil around to get a much more oval ellipse. We can clear it and change the length of our string, change the values of the foci. We can even put the foci on the opposite axis. And now when we trace, we have a vertical ellipse with a major axis that is vertical and a minor axis that's horizontal. So the definition of an ellipse is the set of all points in a plane, the sum of whose distance from the 2 distinct fixed points called the foci is constant. D sub 1 plus D sub 2 has to be equal to the same number consistently. As you can see, our ellipse has some points that are important, plus 2 axes. One of them is the center point. If the major axis is horizontal, the vertices will be to the right and to the left of that center point, equal distance. And the minor axis will have some minor vertices that are vertical from that center point. We have 2 different types of ellipses that we can have. One of them is a horizontal and one is a vertical. When you're looking at the equations, they look very similar to a circle. However, because this is not a constant, an r squared, because these 2 have different values beneath them, we'll have an a squared and a b squared in the denominator. And the equation in standard form will always be equal to 1. The ellipse is horizontal when the a squared is beneath the x minus h squared term. So a and b are fixed. A is always the larger of the 2, and therefore a squared will always be the larger of the 2. When it's vertical, the a squared is beneath the y minus k squared. So a squared moves around, the larger one moves around, based on whether it is a horizontal ellipse or a vertical ellipse. I don't get too hung up about this form. I simply decide, okay, I'm going to remember that if it's a horizontal ellipse, my major axis is horizontal. So my HK is my center, which was consistent with our circle, and then I know that I need to move the square root of a to the right and to the left, square root of a squared to the right and to the left. If it's a horizontal ellipse, I move b up and down and from the center, HK, and then I can figure out what my foci are in just a moment. And the foci are always, always, always on the major axis. If it's vertical, I know that I have a larger value beneath the y minus k squared, and so I'm going to move up a and down a from the center, left and right b from the center, and then we'll talk about the foci here in just a moment. So don't get too hung up on this notation. Simply remember, if the a is beneath the larger value is the squared term is beneath the x minus h, then it's going to be horizontal. Move a to the right, a to the left. My total length of my major axis is twice a. If my vertical is has a larger denominator, if my y minus k has a larger denominator as vertical, And so I'm going to move up and down from that center, and I move up 2, down 2, 2a for my major axis, right to left, right b, left b, so 2b for my minor axis. So how to find the foci? So if we look at this GeoGebra example, and we show ellipse A, actually we'll show ellipse B, you can see that ellipse B has 2 foci listed here. So as I move this point, again, this A, the distance 1 plus distance 2 is consistent. And when I'm looking for my foci, the way I remember it is that because an ellipse has an equation similar to a circle with a plus sign in the middle, then I need to use something that looks like the Pythagorean Theorem. C squared is a squared minus b squared, however. And so the distance between the center and the focus is going to be equal to c, where we take 36 minus 9. So the square root of 27 away from the center, the square root of 27 away from the center to the right. So once again, c squared is a squared minus b squared. It's the opposite sign of what's between our squared x term and our squared y term. And just remember that the focus is going to be on the major axis, c units away from the center in both directions. Eccentricity is given by E equals c over a, and that is going to measure how oval your ellipse is. Eccentricity is always between 0 and 1, and we're going to take that number that we found by subtracting a squared minus b squared, and we'll divide that by take the square root of it and divide it by a to find the ovalness. If something is closer to 0, it's more circular. There's not much difference between a squared and b squared. If it's closer to 1, it's more oval. So we're going to find the center, radius, vertices, foci, and eccentricity of this conic. So first of all, this is not in standard form, so we're going to need to complete the square in order to bring it into standard form. So we'll gather our x's, x squared plus 6x, leave a gap, and we'll gather our y's, 4y squared minus 8y, leave a gap, and we'll take our constant to the other side by subtracting 9 from both sides. Then we ask ourselves, what is the perfect, or the number that we want to add to make this a perfect square trinomial, and half of 6 is 3, 3 squared is 9. And if we add 9 to the left side, we have to add 9 to the right side. However, the second term, this will be an x plus 3 squared. The second group needs to have the 4 factored out, because we have a leading coefficient, so 4 times y squared minus 2y. And when we do that, we have to ask ourselves, what is half of that middle term squared? And we're going to add the number 1 to this side. But when we add 1, we're truly not adding 1, we're adding 4 times 1, so we need to add 4 to the other side. So now we have a binomial squared, another binomial squared, square root of the first, sine of the middle, square root of the last, and 9 minus 9 is 0, plus 4 is 4. So we have an HK, a center, that is -3, +1. -3, +1, we plot that point. I like to call it C for center, so I can keep my wits about me and know where everything's going. This particular conic, we want to take it and finish it off. We have a 4 over here and a 4 here. That tells us it's not a circle. So we're going to divide every term by 4 to get it into standard form for an ellipse, and we'll have an x plus 3 squared over 4 plus 4 over 4 simplifies to 1, so y minus 1, if you want to quantity squared, if you want to put it over a 1 you can, is equal to 1. Now it's in standard form for an ellipse. So we have our center. We know that because our larger denominator is 4, then that means a squared is 4, and this will be a horizontal ellipse. So we will move 2 units to the right of our center and 2 units to the left of our center to get our vertices. I like to call them V sub 1 and V sub 2. And then we will move up 1 and up down from our center to find our 2 minor vertices. Our book doesn't call it that, but we can use that as a frame of reference. And we're going to sketch this ellipse. And this ellipse will have an eccentricity closer to 1 because it's more oval. So we found the center. Our vertices are -5, 1, and -1, 1. Now we need to find the foci. To find the foci, we need to find a squared minus b squared. So we're going to take 4 minus 1, and we will get 3. So if c squared is 3, then c will be the square root of 3. When your foci have values involving square roots, and by the way, we introduced a square root, so we introduced a plus and minus. When our foci have values involving square roots, I'm not going to ask you to find the decimal equivalent to that, and we can write them more compactly than we can the vertices. So we are moving c units to the right, c units to the right of the center and c units to the left. That means that we're going to take that -3 and we're going to add and subtract the square root of 3 that we found when we found our foci. And then we are 1 up. So we can write them in a compact version. -3 plus the square root of 3, 1, -3 minus the square root of 3, 1. So our last step is to find the eccentricity, and eccentricity is always c over a. And our c was the square root of 3. Our a, well, 4 was a squared, so our a will be 2, and we can just leave that as the square root of 3 over 2. Same idea for the second example. We have to gather our x's together, leave a gap, gather our y's together, leave a gap, take the 4 to the opposite side by subtracting from both sides. Factor out your leading coefficient, factor out your other leading coefficient, and then ask yourself, what do you have to add to the first group to make a perfect square? Half of 4 is 2, 2 squared is 4. What do we add to the second? Half of 2 is 1, 1 squared is 1. But we net result added 9 times 4, or 36, to the first group, 4 times 1, or 4 to the second group. So we now have a 9 times an x plus 2, square root of the first, sine of the middle, square root of the last. 4 times square root of the first, sine of the middle, square root of the last quantity squared is equal to, and our net result is 36. To finally get this into the correct form, we're going to divide everybody by the constant. And our conic in standard form is x plus 2 squared over 4. 9 over 36 simplifies to 1 over 4, plus y minus 1 squared over 9. 4 over 36 simplifies to 1 over 9 is equal to 1. This time, my A is beneath the y, so this will be a vertical conic, or vertical ellipse. And my B squared is beneath my x. So my center is HK, -2, +1. My vertex is going 3 to the 3 above and 3 below. So center V sub 1, 1, 2, 3 below, V sub 2. Because B squared is 4, I'm going 2 to the right, 2 to the left, and I'm going to make my ellipse. And then my radius is non-existent again because this is not a circle. Some of our book tends to throw a few circles in here and there. Our center is given, our vertices are -2, 4, and -2, -2. And then our foci are found by taking a squared minus b squared, 9 minus 4. So c will be the square root of 5, and then the negative square root of 5. And the square root of 5 is a little bit more than 2, so we can plot those two foci, f sub 2 and f sub 1. And our foci are going to be -2 and then a +1 plus or minus the square root of 5. Up and down. And then finally, eccentricity if we take c and divide it by a, we're going to get the square root of 5 divided by our a, which is 3. A squared was 9. So our eccentricity is the square root of 5 over 3. So work on the assignment that is either the Desmos assignment or the alternate paper assignment, and I'll be back.